and welcome back to another lecture of Design and Analysis of Experiments, Stat 568. Today, we will be taking the factorial design in a whole new direction. We're going to be cutting it in half, and then cutting it in half again, and again, to get a fractional factorial design. Now, the idea is that a factorial design is really useful. We can test a lot of things, but we need a lot of data collection to do that. And we typically don't want to collect all that data. So instead, what we're going to do is we're going to cut it in half to create a fractional factorial design. And if the data size is still too large, we're going to cut it in half again and again. But we're going to have some interesting problems that arise along the way, because every time we cut it in half, we are going to be overlapping factors with other factors, and that can get a little bit tricky. So let's see what happens there. And welcome back to another lecture of Statistics 568 Design and Analysis of Experiments. Today we'll be continuing our discussion of the factorial design, but instead of looking at full factorial designs, we're going to look at fractional factorial designs, which add an extra complication into the mix, which is that we don't want to test all possible 2 to the k treatments, because 2 to the k could be a lot. And if we're not interested in testing all of the high order interactions, specifically the very high order one, like a k-way interaction or a k-1 way interaction, we don't actually need to test everything. But what's going to happen, all right, is effectively we're going to take the design and we're going to fold it on top of itself, so that every effect gets matched up with a different effect. So ideally what this means is we will be overlapping low order and high order effects. So we have a main effect, which will then be said to be aliased with a high order effect. And then if we get significance in that term, we say, okay, if we have significance here, it could either be the low order one or the high order one, which is giving me significance. And then we just assume it is the low order term, mainly because we typically work under the assumption that higher order interactions are not going to be significant as frequently as lower order interactions or single main effects. But mathematically, we have to decide now, how in the world do we choose which half or quarter or eighth or 16th of the data to actually collect? And that is where we have to study the fractional factorial design. So let's take a look at that. All right, so in this lecture, we will be looking at the fractional factorial design. And roughly, the idea is take a 2 to the k design and reduce it by, I'll say 2 to the q. I think I was using q, or no, p. It was the notation I was using in my notes. P, i.e., cut it in half, p times. And what we're going to do, though, is we need to know how to cut it in half p times, because we can't just start throwing out any data point we want, right? We have to very precisely choose which data point, which treatments to keep and which treatments to throw out. That's the rows in this table that I have here. We have to decide which rows do I want to keep and which rows do I want to remove. So the example is the same 2 to the 3 design that we looked at last time. And the one way that we could consider a fractional design here is to remove row 1, remove row 2, remove row 7, and remove row 8. So what happens if we only take rows 3 through 6? Because that's effectively what I'm doing here. So let's just block that off. not block in the block sense, block in the I'm literally drawing a block around these. Okay, so in this case, the idea is that our data set has now been reduced from 8 to 4. So not a big absolute reduction, right? But it's here just to demonstrate the idea. If we had a 2 to the 10 design, I would have 1,024 data points. So cutting that in half means I'm now down to 512, and I just saved 512 measurements that I don't need to do. That's a lot of measurements. But that also would be a real pain to write in my notebook here. So we're going to do a 2 to the 3 design just for the sake of exposition. But now let's stare at this. Well, what happened? Well, there's a couple weird things that we note. So the first thing that's worth noting is this column here. So, well, first we're going to note that the interaction 1, 2 is only tested at the minus level. And what that means is that we can no longer test for the significance of the interaction of factor 1 and factor 2, because we would need minuses and pluses to be able to compute an interaction effect, because the interaction effect is really just says what's the average of the pluses, subtract the average of the minuses. Well, right now I only have minuses, I don't have any pluses, I can't test this. So the point of this is that can't test it. So we just lost one thing. We can no longer test the interaction between 1 and 2 by destroying rows 1, 2, and 7, 8. Another interesting thing to note is that we have some pairings to take into account. So let's see if I can do this without completely ruining. Well, if we look at columns 1 and 2, we note that whenever 1 is a negative at minus, 2 is a plus. And whenever 1 is a plus, 2 is a minus. So they're actually coinciding. The columns are the same. Okay, yes, they are flipped, but the plus and the minus are just sort of arbitrary designations. That means treatment or not. So I could easily remap pluses and minuses if I really wanted to be different factors. So the idea is that 1 and 2 are actually completely coinciding. Similarly, the same thing happens with 3 and 1, 2, 3 and 1, 3, and I can just draw a circle around these guys, 1, 3 and 2, 3. So the second thing to note is that columns 1 and 2 and let's say 3 and 1, 2, 3 and 1, 3 and 2, 3 coincide pairwise. I.e., we can only test one of them. Well, to be precise, it's not so much that we're only testing one of them, we're testing both of them at once. So if we were to look at the ANOVA table, which I'll draw over here, what we would end up with is, well, 3 rows, right? We now only have a data size n is equal to 4, which means we have 3 degrees of freedom to work with. We can only estimate 3 things. We can only test 3 things. We don't have any degrees of freedom for the residual, so we actually can't run a hypothesis test, or I should say an F test. But ignoring that, because you could replicate a fractional design to get more degrees of freedom, but forgetting that for the moment, the point is that we can only estimate 3 things, and what we get is we get a 1, 2, we have a 3, 1, 2, 3, and we have a 1, 3 and a 2, 3. And this would be the, I guess, the effect. And then the degrees of freedom for each of these is going to be 1, 1, and 1. And then you could feasibly compute a sum of squares for each of these 3 rows. But the point is that even if we had the ability to do an F-test for significance, or if we were to use Lentz method from the previous lecture to test for significance without replicating, then if we got significant in the first row, so let's say if this turns out to be significant, then what does that mean? It means that either factor 1 is significant, or factor 2 is significant, or they're both significant, or they're both a little bit significant, and then they're kind of put in, augmented by being, in this case, aliased together. So that's, I didn't actually write this down, but that's what this is what this is called. It's called aliasing. It's where you have 2 different effects, interaction or main effects, that are now overlapping each other. Like I said at the beginning of the lecture, we basically have taken our design and folded it over on itself. Geometrically, you can think of all of these points, because everything's binary here. So if I have, say, 3, if I have 3 treatments, then you can think of every row as being a vertex of a hypercube, or of actually a cube in this case, just a 3-dimensional cube. And then in some sense, we're deleting some of the entries. Maybe I'll draw that picture just for the geometric minded among us, because I love geometry. What we can do is we can actually think of this design, a 2 to the 3 design, as a cube. And every data point is going to be a vertex of this cube. So it's going to look something like this. If I can, where's that? Oh, that one connects here. Yes, good. Excellent. So we have something like this, and then we would have 3 dimensions to work in. The dimensions might be minus and plus for factor 1, minus and plus for factor 2, and the diagonal, which is a little bit harder to draw here cleanly, but we'll call it minus and plus. I'll just draw it like this, for factor 3. So we have 8 points. Each of those corresponds to one of the data points in our 2 to the 3 design. If I take the fractional design, well, what am I doing? Well, what I'm doing is I'm deleting minus, minus, minus. So we now no longer have this point. I'm deleting minus, minus, plus. So we no longer have this point. I'm deleting plus, plus, minus. So we no longer have this vertex. And I'm deleting the plus, plus, plus point, which would be the far back vertex. So the point is that when I do a fractional design, I'm actually deleting 3 or 4, half of them. I'm deleting half of the vertices of my cube or hypercube if I have 4 or more factors to consider, and I'm keeping the other 4. So that's effectively what's happening, and it's one way to visualize what is going on here. In a way, we're kind of slicing the cube in this case with a hyperplane. It's kind of interesting. I guess in 4 dimensions, it would be harder to visualize. A geometer could probably tell me what I'm doing, but I think you're still cutting the cube in half. I think you're probably intersecting it with some sort of 3-dimensional, you're a 4-dimensional cube getting sort of hit with a 3-dimensional cube or something, but I'm not sure. I'm not really good at higher dimensions, so we'll leave it at 3 for now. But this is what's going on here, and the point is that now we actually have this aliasing that's happening, which means we have overlaps. factors 1 and 2 are indistinguishable. Main effect 1 and main effect 2 are indistinguishable. Main effect 3 is indistinguishable from the interaction effect 1, 2, 3, and the two remaining two-way interactions 1, 3, and 2, 3 are now indistinguishable in the ANOVA table. So again, if we find that one of those rows is significant, we don't know which term it's coming from. It could even be both. They might both be significant, or at least one of them may be significant. If you had a case like 3 being aliased with 1, 2, 3, what you would typically say is that, okay, if that term is significant, we're more likely to believe that the significance is coming from main effect 3 rather than three-way interaction effect 1, 2, 3, because the three-way effect is less likely to be significant than the main effect. But again, when you analyze data like this, you have to kind of work on your feet and think about, okay, if I have significance in one of my rows, what does that correspond to, right? We have to figure that out. Anyway, yeah, so we could write this out mathematically. So what I will say is mathematically, since I basically wrote it out mathematically, let's write that correctly, mathematically, we can also write this out in an equation by looking at the computation of the main effect like we did, I believe, 2 lectures ago. So if I want to compute the main effect here for factor A, what I'm doing is I'm just averaging all of the measurements, all of the observations where A takes the value of plus, and then I'm subtracting all of the measurements where A takes the value of minus, just like we did 2 lectures ago. But what we note is that that coincides with the average of the observations where B takes the value of minus. I switched, I see. In my table here, I have 1, 2, 3. In my table on my notes, I have A, B, C. So I'm going to switch back to 1, 2, 3 to coincide with my written notes here for the lecture. So 1. So mapping 1, 2, 3 to A, B, C and back again. So the idea now is if I want to compute the main effect for factor 1, it's just going to be the average of when 1 is equal to plus, which is observation 5 and 6, and when 1 is equal to minus, observation 3 and 4. Well, this is the equivalent to looking at the average of the observations where factor 2 is equal to minus when factor 2 is equal to plus. And this just happens to be the negative main effect for 2. So if we're, again, trying to compute the main effects for 1 and 2, we get the exact same thing. There's a sign flip, which is just based on the way we assigned pluses or minus ones. But ultimately, that doesn't really matter for our purposes. We just want to know, are these main effects significantly different than 0? Everything's symmetric here. So if we're a few units above 0 or a few units below 0, it's going to be the same thing. But yeah, this is the key thing to look at. And just to write it down, even though I said it out loud multiple times, we call this overlap aliasing, which is a term that you hear in things like signals processing. If you're a gamer, you've probably heard about anti-aliasing and things like that. It shows up here in a similar, maybe discrete notion. Again, the idea that we are now overlapping our design with itself. So the way we denote this, so I should also say we denote such designs as, in this example, well, we'll just say in general, 2 to the k minus p designs, i.e. k factors and p, I'll say aliasing relations, which we'll discuss in a second what I mean by that. But our example, e.g., is a 2 to the 3 minus 1. So you always write it like this. I mean, yeah, 3 minus 1 is 2, but in this case, we're going to say it's a 2 to the 3 minus 1 design to indicate that there are 3 experimental factors and 1 aliasing relation. The aliasing relation we actually have here is we're going to denote 1, 2 as equal to I, the identity. So this is going to be the aliasing relation, or equation, or whatever you want to call it. I guess defining relation is what I also called it in my notes. Mainly because it's going to generate a group. Once again, another mathematical group is coming in to play with us, so we'll have fun with that. But yeah, so this is also called the defining relation. And as you can imagine, when you have -2, -3, -4, -p, you're just going to have more and more relations all tacked on to each other. So we'll be doing lots of examples of that. But yeah, basically this relation here corresponds to the idea that when I look at the remaining column up there circled in green, I get the same symbol minus for all of them. So I have to account for that. I guess technically, maybe it should be -I to be precise because of the specific way I deleted entries. If I deleted 3 through 6 but kept 1, 2, and 7, 8, then I just have pluses in the column. So, but roughly it's kind of an equivalent thing. Whether you leave minuses or you leave all pluses in the column, you're still going to be testing. You're still going to have the same aliasing relation, so it's not going to really matter, until we do de-aliasing. So that'll be a whole nother thing. All right, so where do we go from there? Well, so again, typically we actually wouldn't want to do this. So maybe I should, why don't we say, typically we don't want two main effects to be aliased. Because typically when we're running an experiment, the main effects are the main things we want to test for significance. And if two of them are aliased together, well, now we don't know which one is significant if either. And you can get, in certain rare cases, you could have effects that cancel each other out when they're aliased. It's not as common because it has to work just right. But if you have main effect 1 going in one direction and main effect 2 going in a different direction, they can actually cancel each other out. And then you might detect no significance when you would actually get significance in both 1 and 2, just in opposite directions. So typically we don't want that. So a 2 to the 3 minus 1 should have defining relation I is equal to 1, 2, 3. And if we set I equal to 1, 2, 3, we have destroyed our ability to estimate that three-way interaction term, but we typically don't care about the three-way interaction term, or I should say we care the least about the three-way interaction term. Then we get aliasings, I guess, of, well, what? We get 1 is aliased with 2, 3, 2 is aliased with 1, 3, and 3 is aliased with 1, 2. And we'll discuss a lot more about this in the next subsection, but I just wanted to explain that if you had a design, this would be the best way in some sense to create a fractional 2 to the 3 minus 1 fractional factorial design, because now all the main effects are aliased with a two-way interaction effect. It's not great, but it's better than the alternative, which is having two main effects aliased together, which is not going to be a good time for anyone. At least here, it's just main effect aliased with a two-way effect. If we see significance in one of the rows, we could attribute it to the main effect over the interaction effect. So it's kind of a way to test the main effects, especially if we don't expect there to be any interactions, because we couldn't differentiate the significance of a main effect or versus an interaction in this type of design. But again, typically this is only it would only take 8 observations to do the full factorial design. So in practice, you probably would just test all 8. But again, the thought process is that when you have higher order, when k is larger than 3, it can be very valuable to run a fractional factorial design and save yourself a lot of headache. So yeah, I have an example, but I'm going to save the R examples for the end. I just keep pushing them off, but I swear we will get to them maybe at the end of this lecture if I don't talk too long about all this stuff. But yeah, so roughly, where did I get these things from? Well, let's take a yeah, let's do another. Let's do a better example. So, well, let's do both examples, right? You know, why do we have to choose? We'll do both examples. So if we consider this 2 to the 3 minus 1 design with I equal to 1, 2, 3, this is a group. It's called it's called the defining contrast subgroup. This is a very boring subgroup. It just has 2 elements in it. It has the identity, because the identity is always there, and it has the element 1, 2, 3, which is its own inverse. So remember, in group theory, we need to be able to multiply elements in our group together, and we should get another element in our group. So if we take 1, 2, 3 and we square it, well, oh yeah, wait, how do I want to write this out? I guess writing it out as equal to the identity is a little bit confusing, because what we're doing is we're aliasing it with the identity, but I should actually do a better job at writing this out more precisely. The defining contrast subgroup is going to be I, 1, 2, 3. So it is a group with 2 elements in it. This is the defining relation. And what it means is that we now have a mathematical group. It has 2 elements, and what we're going to do is use that mathematical group to determine all of the aliasing relations that are up here. So I think what I really should say is, this is technically an aliasing relation, but any aliased effects are an aliasing relation, not just the one with the identity. So we're going to keep working through this, and hopefully this makes sense, but definitely ask me questions, because this can get a little bit confusing as we go through it. So do talk to me if this doesn't make sense. Anyway, the idea here is that now what we can do is we can take our main effects 1, 2, and 3. And what we do is we multiply them. Well, we can multiply them by the identity without changing anything, right? Well, because of our aliasing relation, or our defining relation at the top, we know that multiplying by the identity is the same as multiplying by 1, 2, 3. So I have 2 times 1, 2, 3, and 3 times 1, 2, 3. Now, every element is its own inverse. So if I write this out in excruciating detail, I get a 1 squared, 2, 3. I get a 1, 2 squared, 3. And I get a 1, 2, 3 squared. But the squared terms are all the identity, so they drop out. and I'm left with the relations, the equations that I had right above there with those red arrows pointing at them, which I think is a bus line here in Alberta. But anyway, side tangent. So by using the defining contrast subgroup, we can recover the relations from up above by just taking the main effects and multiplying them by both elements of the group. Because if I is equal to 1, 2, 3, then that means that 1 times I is equal to 1 times 1, 2, 3. And if we apply the same group relations here, we end up with just a 2, 3, and we can find out all of the aliasing relations within this design. Now, what we can do is we can make this more complicated, because of course it'll be more complicated if we consider a 2 to the 5 minus 2 design. So this is 5 factors, 2, I should say defining relations, I think, to be precise here. 2 defining relations and a sample size of 2 to the 3, which is 8. So the sample size is only 8. So that's kind of neat. That means I'm going to test 5 different binary leveled factors on only 8 observations rather than on 32. So that's a pretty good savings. But again, we're going to get a bunch of aliased terms here. And the aliasing is more complicated because if I alias with a single, if I have a single aliasing or if I have a single defining relation, I now have pairs of aliased effects in my design. If I have 2 defining relations, I now have 2 to the 2, which is 4, I guess. Is it minus? No, 4 factors all aliased together, or effects all aliased together. So let's do an example of that. Let's say if we have defining relation I is equal to, I think I had 1, 2, 3, and 3, 4, 5. No, not times. 3, 4, 5. Well, if I have all of these, then remember, a mathematical group says that I should be able to multiply any 2 elements in the group together to get another element of the group. So the elements 1, 2, 3 and 3, 4, 5 act as the generators for the group. And if I multiply both of those together, I get the third element of the group. And that element is 1, 2, 4, 5, because the 3's cancel out with each other. Remember, they're an element of order 2, so if I square them, I guess idempotent, right? If you square them, you get the identity, so they cancel out. So that means that I actually have now the DC, defining contrast, DCSG, defining contrast subgroup is going to have 4 elements in it. The identity, the 3-way term, 1, 2, 3, the 3-way term, 3, 4, 5, and the 4-way term, 1, 2, 4, 5. So what does that mean for our design? Well, that means that if I take the main effect 1, it is now going to be aliased with what? Well, what I would do is I would multiply 1 by 1, 2, 3, and I get a 2, 3 out like I did last time. But now I take 1 and I also multiply it by 3, 4, 5 to get a 1. I should put equal signs here to say that in our design, these are all equal. We get a 1, 3, 4, 5. And then I multiply it by this last term and the 1's cancel out and I have a 2, 4, 5. So now I have basically 4 effects, interaction effects, and a main effect, aliased together. And the same intuition follows from above. If this would correspond to a single row with a single degree of freedom in my ANOVA table, in R, it would probably just default to calling it factor 1, the main effect, because R will probably just take whatever the first thing is and treat it. But you have to remember that factor 1 is aliased with 2, 3, and with 2, 4, 5, and with 1, 3, 4, 5. So if you get significance there, you have to consider that it could be coming from other terms, not the main effect the main effect for factor 1. Though, again, we would typically assume that's where it's coming from, but it is aliased with a two-way term, 2, 3, so it's not unreasonable, especially if factors 2 and factor 3 are very significant, that factor 2 and factor 3 have a significant two-way interaction. So again, there's a lot of art to interpreting the data once you've actually seen it, once you've actually run your analysis. We just need to make sure that we know what we're looking at when we stare at an ANOVA table in R, because it's not going to tell you what all these relations are. You have to be able to figure them out on your own. Hence, if we continue working through this, we find out that we get a 2, and then if we find out what that's aliased with, we get a whole bunch of other terms, 2, 3, 4, 5, we get a 1, 4, 5, and if we do 3, we get a 1, 2, we get a 4, 5, and we have a 1, 2, 3, 4, 5. The 5-way term emerges. Factor 4 is aliased with 1, 2, 3, 4, is also, or main effect 4, I should say, with 3, 5, with 2, 5, and factor 5 is going to be aliased with 2, 3, 5, with 1, 3, 4, and with 2, 4. Okay, so what does that get us? Well, that gets us 16 different effects that have been aliased together. So what do we have? So let's count, because counting in this course always will save you from missing things. So far, we have 16 effects here. And if we count our defining contrast subgroup, we have 3 effects from that. Because we have the identity, which is just the identity, and then we have 3 terms that are aliased with the identity. They're just completely obliterated from our design. We can no longer test them at all if we were to run this design. So that gets us 19, but we know that a 2 to the 5 we should have 31 in total, which is 2 to the 5 minus 1. So what does that mean? Well, that means we're missing 12 terms here. And the best way to do that would be to start looking for interactions, because I have 5 choose 2, which is, 10? So 5 choose 2 is 10. I have 10 different two-way interactions. If I count them, I have 1, 2, 3, 4, 5, 6, 7 that have already occurred. So what other two-way interactions are we missing? We have 1, 2, 1, 3, but we don't have 1, 4 yet. So we would get 1, 4. And if we multiply this out, 1, 4 is aliased with 2, 3, 4, is aliased with 1, 3, 5, is aliased with 2, 5. All right, so that brings us up to, 9 two-way interactions, but I still don't see 1, 5 in here. I didn't actually write this all out beforehand, so let's hope that we can fight our way through it. All right, 1, 5 is aliased with 2, 3, 5, is aliased with 1, 3, 4, is aliased with 2, 4. I made a mistake somewhere because I see 2, 4 right up here. 5 is aliased with 1, 2, 4. There we go. Correction. Like I said, it's pretty easy to mess one up here, so it's always good to count. Now we got another 8 terms here. So we haven't quite gotten our 12 yet, right? Because we have 19 plus 8 is going to get me 27, which means I'm still missing 4, which means I'm missing one more aliased group. I think I have all the two-way terms now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So I have all of the two-way terms. There's probably a missing 3-way term in there. There should be another 10 of those, right? Because I think 10 choose or 5 choose 3 should equal 5 choose 2, right? By symmetry. Am I doing that right? I think I'm doing that right. Anyway, let's see what we got. Do we have a 1, 1, 2, 3? We have a 1, 2, is 1, 2, 4 in here? 1, 2, 4 is here. It's 1, 2, 5. I probably should have organized this better beforehand rather than doing it live, but luckily I don't think I see 1, 2, 5 anywhere here. Excellent. So I found it fast. 1, 2, 5. And 1, 2, 5 is aliased with 3, 5. Oh, but 3, 5. Was there a two-way term that did I miss a two-way term? Maybe I miscounted. Oh no, 3, 5 is here. And 3, 5 should be aliased with 4, but 3, 5 should also be aliased with 1, 2, 5, which means I messed this up, and this is supposed to be a 1, 2, 5. Ah, yeah, I had 2, 5 in there twice. It's like a big puzzle that you just have to fight your way through. But that's actually good because it makes me think that we're missing a two-way term now, and they're easier to find. 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. So that means, let's see. We have 2, 3, we have 2, 4, and 2, 5. Do we have 3, 4? I don't see 3, 4 hiding in here anywhere. Let's circle them because it's going to make it a little bit easier to find them. We have 2, 3. We have 1, 3. We have 1, 2. We have 1, 4. We have 1, 5. We have 2, 4. We have 2, 5. We have 3, 5. We have 4, 5. I don't see any 3, 4 floating around. So the last two-way term we need is 3, 4. That's going to be aliased with 1, 2, 4, which I feel like I wrote before. Ah, yeah, 5. 5 is aliased with 1, 3, 4. 5 is wait. 5 is aliased with 3, 4. Ah, I was making a mistake. It's these middle columns that I messed up. Or middle rows, I should say. Yeah, 5 is aliased with 1. I see. I turned 5 into 1, 5. So this is supposed to be a 1, 2, 3, 5. And then a 3, 4. And then a 1, 2, 4. Yeah, this is good times, right? Okay, so we have all of our two-way terms. We have many of our three-way terms. Let's highlight them in blue to try to figure out what's missing, because we should be missing one more set. It's probably going to be like 3, 4, 5, which I don't see anywhere in here. Or no, 3, 4, 5 is already up here. So we have 3, 4, 5. We have 1, 2, 3. We have 2, 4, 5. We have 1, 4, 5. This one, that one, that one, this one. 1, 2, 3, 4, 5, 6, 7, 8, which means 2 of them are missing. And I'm going to guess that it's going to be something like 2, 3, 4. Does that exist anywhere? I don't see any 2, 3, 4s. All right, let's try 2, 3, 4 to end this. So we have a 2, 3, 4. That is going to be aliased. Ah, no, that's going to mess it up again, right? Because 2, 3, 4 should be aliased with 1, 4. And 1, 4, 2, 3, 4 was... Oh, no, we have all of those terms. Look at that. We have all of the three-way terms, which means it's a four-way term that we're missing. There should only... Did we get all the terms? 1, 2, 3, 4, 5. No, we're still missing a whole collection of... I feel like I'm missing something here, right? Because if we have a four-way term would have to be aliased with a two-way term. Oh no, 1, 2, 3, 4, 5, 6. No, we have everything. That's the problem. We have everything, and I've been looking for something that doesn't exist. Because we have four-way terms, 1, 2, 3, 4, 5, and where in the world? Oh yeah, 1, 2, 3, 4, 5. Shouldn't there be a 6? Oh no, of course, 5 choose 2. Right, we got this. Okay, so I think we counted everything. Then why is my count off? It should be 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. 7 times 4 is going to be 28. Yeah, so I just miscounted. Oh, because I have 5 rows of main effects, so it's not 16, it's 20. All right, well, that's recorded forever. So counting, it's harder than it looks. Anyway, the point is that now we have all of the terms accounted for. So what does this mean besides looking like a terrible mess? Well, what it means is our ANOVA table will just look like, well, basically it's going to have 5, 6, 7 rows. It's going to have 7 rows for 1, 2, 3, 4, 5, 1, 4, and 1, 5. So you're only going to have 7 rows, but you have to remember that they're all going to actually not just be a term, an effect, but an aliased group of 4 effects. Right, and that's what happens. So we've basically taken our design and we folded it over once, and then we folded it over again to cut it in half and cut it in half. Every time we fold it over, we lose one of the one of the interaction effects gets aliased with the identity. And then when we alias it a second time, we now get 2 more terms aliased with the identity. So, all right, let's do the final count and then make sure we got this right. So what I have is I have 7 groups of 4 aliased effects, which is 28. So that's the first part, plus 3 effects aliased with identity I, and that's going to account for everything in our design. So in summary, this is one way that you can get away with testing 5 main effects in a factorial design only using 8 data points if you're okay with some of this extreme aliasing that's going on. Now, again, the bigger your design, the more complex things get, but the more benefit you get from looking at a fractional design, because you typically don't see people just running a full, 2 to the 12 design. They'd probably do like a 2 to the 12 minus whatever's feasible design and start dropping out different terms in the model. You just have to be very careful when you do that, because of these aliasing relations, and they can get really complicated, as you can see just by me spending the last 15, 20 minutes trying to count every single of these 31 different terms in the model. And then note that the identity would be the 32nd term, which also kind of corresponds to the global mean and everything like that. So there's a nice interpretation to all this. But anyway, that's what we got here for our 2 to the 5 minus 2 design. So that leads to an important question. Yeah, we'll save maybe de-aliasing for next time. The important question is, how in the world do we decide what to pick for our defining contrast subgroup, right? Because all of this mess came from the defining contrast subgroup here at the top of the page, the DCSG. And we chose that. I mean, I chose that just to give an example to work with, but should I have chose that? Is there a better way to do it? Are there smarter choices? Are there less smart choices? We should look into that and figure out what's going on. So this leads to a bunch of definitions, which should hopefully give us something to ground us with, rather than being stuck with all these crazy numbers floating around. Definitions. So first of all, we have to talk about a clear effect. So a main or two-way interaction effect is called, we'll switch colors, clear if it is not aliased with any other, I think it's two-way or one-way or two-way, yeah. If it's not aliased, yeah. If none of its aliased effects are one or two, yeah. If it's not aliased with any other main or two-way effect. So that's a desirable property because, again, we're always working under this assumption that the higher the order of the interaction, the less interesting, the less interpretable, the less likely to be significant it's going to be. So a nice property of a design would be to make sure that the main and the two-way effects, the most important ones we're going to test, are not aliased with any other main or two-way effects. This would be called clear. In the case of the design up here, nothing is clear because we have one-way main effects aliased with two-way effects, and down at the bottom, the last two rows have two-way effects aliased with two-way effects. So in this case, none of these would be clear, but that's okay. I think that's the best you can do for a 2 to the 5 minus 2 design, but it is a criterion that is worth noting. Right, and then that leads to strongly clear. So a main or two-way effect is called, let's say, strongly clear if it is not aliased with any other, I guess, main two-way or three-way effect. All right. So that just means we have an even stronger setting where the main and two-way effects are also not aliased with any three-way effects. So it really means that if we get significance in that row, it's either going to be the main or two-way effect, or it's going to be some fourth or higher order term. And once you get to fourth or higher order, you're really starting to get out there into where you don't suspect there to be any real significant interactions. So that's another thing. Okay, yeah, we already determined what a defining contrast subgroup is. See, I am using 2 to the Q in this part of my notes. So I'm going to say that just to write it all down again. The defining contrast subgroup for a 2 to the K minus Q design has 2 to the Q minus 1, we'll say, effects in it, plus 1 for the identity. Again, in a group theory context, what we're doing is we're taking the order 2 cyclic group, if that's the right terminology, and we're basically multiplying it by itself Q times. So what we get is we have like Q different order 2 terms, and then we can consider all possible products of those generators. Right, and that's going to get us something. Again, group theory, it's okay. I'm guessing not everyone's seen it, so we're not going to go into all the crazy details of that. But just to consider the fact that this is a subgroup of the original 2 to the k minus 1, I guess, columns of the full design. So if you recall from the last lecture, I said that if you have a full factorial design, you can think of all the columns as the individual elements of a mathematical group. And then we also would include another column, which would be the all ones column for the identity. Now, this defining contrast subgroup is a mathematical subgroup that lies within, because we're basically taking certain columns and considering the case where they're only ever set to be a certain value, and that's kind of aliasing them with the identity, right? Okay, so we had the example that we did, and then we have to discuss the idea of resolution. So, well, maybe I should say the resolution of a 2 to the k minus q design is the length of the smallest, I guess, element effect in the DCSG, defining contrast subgroup. So very often you can find papers that talk about, we have a resolution 5 design, we have a resolution 4 design, resolution 3. Typically you don't want to go below 3, because if you have a resolution 2 design, that means you have an order, a length 2 term in your defining contrast subgroup, which means you're going to have two main effects alias together. So resolution 2, bad. Resolution 3, okay, not great, but it's not bad. So this leads to the idea of typically we want a maximal resolution design, which really just means of all the possible 2 to the k minus q designs that you could pick, and there's a bunch of them. I guess there's, well, it depends on how many ways you can choose generators uniquely for the defining contrast subgroup, which I'm not going to do on the fly in my head right now. But the idea is that we'd want to pick one of those that gives us the maximal resolution. So if we go all the way back up to what we did at the beginning, when I gave you that first example here, I had a resolution 2 design in this first example because 1, 2 is aliased with the identity. But when I went down here, I now aliased 1, 2, 3 with the identity, so I had a resolution 3 design. So the point is that this one is actually better than this one up here in green because it's resolution 3 versus resolution 2. Higher resolution means main effects are, and means lower order terms are aliased with higher order terms. The higher the resolution, the more of a gap there is, and the more desirable the design is. All right, and now we're in our studio because I figured we could continue talking about the notes, which would take us into the idea of de-aliasing and optimal design, and there's lots of other things to discuss, but it's good to maybe take a moment and go back to the full factorial designs of 2 lectures ago and 1 lecture ago and try to consider what happens when we actually look at this data in R. So we're going to start by looking at some simulated data, and then if we have time, maybe we'll go and look at a real agricultural data set from, I don't know, probably like 50 to 70 years ago, because that's when all these data sets seem to have been collected. So first, let's get a little bit of room here. This is just some sample code that I created. That actually is what I'm using in my online lecture notes if you're reading along with those. So the first thing I'm going to do is set k is equal to 4. I'm going to use the expand grid function to create all of my combinations. I don't want to type there, I want to type down here. to show you what expand grid does. What it does is it now does every possible combination here of 0 and 1. So in this case, I'm using 0 and 1 rather than plus or minus 1, but it's really the same thing. They're just factor levels. They're not specific numerical values. So then I create main effects. So here what I'm going to do is say that A is 0, B is 0. So those terms, no effect. C is going to be 1 and D is going to be 2. So factor C is going to have some sort of significant effect, and factor D is going to have an even more significant effect. Then we can also include some interactions. So here, just to be tricky, I included an interaction between A and B, even though notably I did not include any main effect for either A or B individually. AC, there's no interaction, and AD, there's a -1 interaction. So those are going to be my main interaction effects. Then I set the random seed so that I get the same results every time. And we go through here. So first of all, I'm just basically I'm creating values Y. So first of all, I'm adding main effects in. The next thing I'm doing is I'm adding in the interaction effects, and then I'm adding in some random noise with a variance of or a standard deviation of 0.1, just to give us some random noise, because we need some random noise or else this is going to look really strange. But not too much random noise, so we can really detect what's going on here in our data. All right, so we have that. So now we just shove everything into a data frame, and I need to tell it that these are all going to be factors. So that's what that line did. And now we can look at our data frame dat. And there we have it. So we have factors A, B, C, D, and our response variable Y taking on real numerical values that seem to range approximately from slightly below 0 to about +3 or so. Well, we can fit a model, but first, let's look at the data. Let's just plot this and see what we get. So what I can do, right, is I can plot data, let's say A, against data Y. And what I get is, okay, so there, I definitely don't see any effect there. The two black lines are basically at the same position. For B, now for B, that's quite interesting. We actually see that there is a difference there. The question is it a significant difference or not? For C, we see now, once again, a difference between the two box plots, but is it significant or not? We'll have to test to find out. And D is very far removed from each other. So D is supposed to be our most significant effect, our most significant main effect, which you can kind of see here by the fact that the two box plots are starting to really separate. But it's better to actually just run a full factorial design and see what we get. And this is what we get. So again, we don't have any degrees of freedom left for the residuals when I do the design this way. What we do get, however, are sums of squares and mean squares. Mean squares is kind of boring because every term has 1 degree of freedom, so the mean square and the sum of squares is the same thing. But regardless, the point is that we can kind of scan down the column and notice some things like, oh, look, A, well, first of all, a lot of these are really close to 0. So if they're really close to 0, that's kind of hinting that there's nothing interesting going on here. There are a few that are above 1. So AD is above 1, AB is above 1, and B alone is above 1. Meanwhile, C is actually at 3.6, and D is the biggest by far. It's 8.9. So now it makes us think that, okay, D looks to be a lot bigger than the rest, and so does C. B is kind of big, even though we know that's actually would be a false positive there. But A, B, and AD are also maybe significant here. It's hard to tell. The rest of them have extremely small sums of squares, so we don't want to, we're pretty sure there's nothing interesting going on there.
Nevertheless, what we can do is we can also visualize this in different ways. Now, when we just type in summary, we get an ANOVA table. It's going to give us sums of squares. If we type summary.lm, what we end up with is a linear model, which is going to tell us all of the main and interaction effects. So in this case, the intercept kind of corresponds to the, I guess, the 0 setting for all of the factors. And then A1 is going to be the difference between A0 and A1. So this is like the main effect for A, for B, for C, for D. Now here we don't see we don't see a large estimate for B, which is interesting because for some reason we actually saw a decent sized sum of squares over here. So that's a little bit interesting to take note of. But here we see, okay, which effects, main or interaction, seem to be large? Well, C is about 1. We know the answer should be 1, so that's good. D is 2, that's good. AB is close to 1, which is the right answer. AC is a little bit negative. It should be 0, but we don't know that a priori. I just know that because that's how I generated the data. And similarly, AD is close to -1, which is like the right answer. And all of these are supposed to be 0. So again, we wouldn't know a priori if, say, -0.21 is close to 0 or not. But we can still visually stare at this and get some intuition about what's happening with our data, even if we can't run a hypothesis test. Notice that there's no standard error, thus there's no t-value, and thus there's no p-value. So we're missing a lot of things in our table here. Now, we can take all of these coefficients and we can plot them with the QQ norm function. And this is what we get. And I think this is quite interesting because here you can very visually see that there are there's one term up here, which happens to be factor D. Now that one's really far above the rest. You've got these two here, which I don't have. Oh, that's right. I have the code here to label it. So why do I even have to guess? We can just label them all. Luckily, I was thinking ahead when I wrote this code, I think 2 years ago or 3 years ago now. So factor D is popping up here, and that looks pretty different from the rest. The same with C and AB. Like when you stare at this, you kind of think, okay, there's definitely something going on with C and AB, and then there's something going on with AD here, and the rest just seem uninteresting, right? It's just this line pretty close to 0. Now remember, this is a normal QQ plot. What we're assuming is that, I guess I didn't actually normalize these, but the idea would be that if we were to, in some sense, normalize this, we should see coefficients that look like random noise, that look like random normal noise, if our errors are in fact epsilons are actually normal. We can also use lengths method. So lengths method is hiding in the BSMD library. I forget what that stands for. It stands for something. Of course, I don't have it installed on this laptop, which is very strange, actually, because I'm sure that I've done this example with this laptop, which I've had since I started teaching this course in 2018. So why that's the case, I'm not sure. Maybe I reinstalled something and it decided that it got deleted somehow. Regardless, we can bring it back. And now we can have our BSMD library. Let's see what that is. Bayes screening and model discrimination follow-up designs. I actually don't really know what else lies in this library. There's probably a lot of other really interesting things in there. We're just going to use it for lengths method. Because when I apply lengths method, it just gives you a plot. And here, we actually see once again, lengths method can get this plot can get kind of nasty when you have lots of high order terms, because it's just going to type them all out on the horizontal axis and they start to overlap each other. But here, what we do is, remember what lengths method is doing from last lecture. It's estimating the effect, main or interaction. It's estimating a pseudo-standard error. Then it's dividing one by the other to get a t-like statistic. Then it plots them all in this kind of bar-like plot, where here we once again see that C, D, AB, and AD are all passing both thresholds. Now, length plot is going to give you two thresholds. It's going to give you the, I forget what ME stands for, marginal error rate, and simultaneous error rate, I think, is SME. Regardless, the closer in line is basically the individual error rate. It's saying with probability, I think it defaults to something like probably 5%, because yeah, alpha defaults to 5%, because of course it does. It's always 5% in statistics. But the point is that any line that surpasses the first dashed line here, which is slightly less than 1 in magnitude, we can reject that at the individual error rate of 5%. That's not corrected for multiple testing. The higher up line, the second dashed line, is corrected for multiple testing. So it's saying that these we can reject at the sort of experiment-wise or the simultaneous confidence test size or confidence level of 5%. So what it means is there's only a 5% chance that any of the four of these are a false positive. And notice that all the other terms don't even surpass the individual error rate, let alone the simultaneous error rate threshold. You could have the case where one of these does surpass one and not the other. And again, you have to sort of think on your feet and decide, well, what does that mean? Do I want to determine, like declare there's a significant effect there or not? It can depend a lot on where you go next with your experiment, right? Data rarely just lies on a computer like this. It's going to lead somewhere. The significant terms are going to tell us, okay, what do we do next? Do we change some policy? Do we do follow-up experiments to learn more? You know, what do we do once we've analyzed our data? And that's why, again, a lot of these are just rules of thumb, and they're just kind of, I don't want to say ad hoc, 'cause they're not ad hoc, but they're just kind of there to guide us. In this case, we see four significant terms that seem pretty significant. So that might lead us to say, okay, let's do some follow-up study on those terms, or maybe that'll be all we need to then change the way we do our farming or our medical science or whatever. Anyway, yeah, so that's what goes on there. Now we can also do a fractional factorial design. So here, what I'm going to do, and you can see in the code up here in the top left, I wrote in a comment, I is equal to ABCD. So what I did was I aliased the term ABCD with the identity. That means we have a resolution 4 design. Typically, if you're going to just have a 2 to the k minus 1, the one thing that you should alias with the identity is the highest order term you have. That's when you get to these optimal choices for a 2 to the k minus q design, it can be quite complicated. But at least when it's a 2 to the k minus 1, there's the obvious choice, which is alias the highest order term with the identity. That will get you the highest resolution you possibly can for your design. So I did that here manually by saying, go to my data table and only take rows 1, 4, 6, 7, etc. So I only take half of my data table now, and I can fit model 2 based on only half of the data table. But first, let's just look at that data table to see what DAT2 looks like. Okay, so now, yeah, things have changed a little bit. Again, what you'll notice is that if you add up every row, you're always going to get an even number, right? You're going to have either all zeros or 2 1s and 2 zeros, or you're going to have all 1s. So that is because we aliased this 4th order interaction with the identity. It's quite interesting, actually. It means that, because what is a 4th order interaction telling us? It means that either all the terms agree, or none of, or no, either all the terms agree, like 0, 0, 0, 0, 0, 0, 0, or 1, 1, 1, 1, or two agree and the other two agree, but they differ. So you have 2 1s and 2 0s, right? This is what the fourth order term is doing. It would compare all of those observations to the ones where you have odd sums, where the number of ones sums up to either 1 or 3, which are the only odd numbers between 0 and 4. Almost there. Just got to hold out a little bit longer with this voice. Anyway, we should look at this model to see what happened. Okay, so now we only have, well, half of the entries that we had before, because remember, all of these main effects are now aliased with a third order interaction. And you might want to try to write this out yourself at home just to see if you can identify the aliasing relations that happen here. Each of these two-way terms is aliased with another two-way term. So D still has a pretty big sum of squares. C does as well. B is a little bit below 1. AB is now not as obvious what's going on there. And the same with, I think, BC. What was the significant ones? I even forget. I think it was AD is supposed to be significant, but AD no longer appears here. So what is AD aliased with? It's aliased with BC. So this row is actually AD and BC at the same time, but R just picks whatever it picks, and it picked, in this case, BC to represent that row. Yeah, good. Okay, so now we have that. Let's look at the linear model, the estimation of the main and interaction effects. So again, we have even more NAs now because we can only estimate half of the main and interaction effects in our model. And now the terms are a little bit less obvious. Before, they were all pretty close to 0 except for the significant ones. Now, and this is a really weird thing that happened, C and D are no longer close to 1 and 2. They've now, for some reason, both averaged and look like they're about 1/2. I find that to be a bit peculiar. I still haven't quite figured that one out. AB still looks like +1, but now BC looks like -1, and BC is not significant. AD is the significant one, but we no longer can detect that because we have to identify that actually these two terms are aliased together. So the significance here could be coming from BC, but it could be coming from AD. In this case, it's actually coming from AD because that's how I generated my data. But without more data points, we wouldn't be able to de-alias that. Yeah, no, I'm not going to do this. This was just where I replicated this thing lots and lots of times. But actually, why don't we try lens plot again, just for fun. Not with that, though. What I want to do is I want to do this with model 2. I wonder why I didn't do this the last time. I'm guessing it's going to not work. Oh, okay, that's why, because it's going to get super mad at me, probably because, oh, I think there's only 7 now. Yeah, I think that's why I didn't include lens plot, because it looks terrible. It looks absolutely terrible here. The problem with lens plot is that even the marginal error, or the individual or marginal error rate here that does not account for multiple testing is still way above any of our estimated points here. The problem is our pseudo standard error is quite large now. Note that the pseudo standard error is now 2.9, whereas last time the pseudo standard error was 0.26. Remember, what's the pseudo standard error doing? It's trying to estimate the standard error. I know what the standard error is. It's 0.1 because that's how I generated my data way at the top of this design, right? This is the standard deviation here, 0.1. So the pseudo standard error kind of overshot a little bit the first time. The second time, it really overshot the value. Again, the pseudo standard error calculation is best when you have lots and lots and lots of effects and only a few of them are significant. The problem is now I only have 7 things here, and 3 of them, actually 4 of them, are significant. So this is a terrible setting to use lengths method. It's good to be aware of things like that. If I had a much larger design, even in a fractional factorial design, larger in the sense that more data points, I would suspect this would work better. We could try that out, but I've been talking for a lot now, so I think you probably need a break. My voice needs a break. We'll pick up again in the next lecture, and then we're going to continue our discussion of fractional factorial designs. What we'll be doing is actually looking at de-aliasing and follow-up studies, because one of the nice things about a fractional design is that you're not actually done when you run it. If you run it and you find some significance and you don't know where that significance is coming from, you can do a follow-up study to de-alias the effects that are aliased together. Remember what I said, if you get the significance in a row, you don't know which term it is. It could be 1 of 2, 1 of 4, 1 of 8. But you can go back and try to de-alias those terms, break them apart in order to determine which one is the significant one. And we'll talk about that in the next lecture. So see you there.